So today I am honestly very excited because I will be talking about something about which I am too much obsessed, and that is the celebrated Navier Stokes equation. If you have studied the fluid mechanics course from any branch and you have not studied Navier Stokes equation well, then I cannot say that you have studied fluid mechanics. Now, if you are thinking that now this guy will be teaching the fluid mechanics in this video, I don't need that. Or this guy will be maybe talking about the most advanced thing about Navier Stokes equation. I don't need that because I just only care about cracking it. So please don't leave now. Wait for 5 to 7 more minutes. If you are someone who loves mechanical engineering, especially fluid mechanics, then this video will be heaven for you. But if you are someone who just cares about cracking it, maybe in mechanical engineering, civil engineering, aerospace engineering, PI, that is the production engineering, engineering science, or any other branch which has the fluid mechanics subject, then also I will show you that how this beautiful equation can make your preparation simpler. Those of you who always argues that, oh, there are so many formulae, I can't memorize all these things. So I can show you that this equation can help you to memorize all the formulae. So please stay tuned. Now, what can you expect from this video? First of all, I will give a brief intro about Navier-Stokes equation. No, I will not give the derivation because it will take almost 2 to 3 hours at least. So I will talk about some facts which are important both in terms of GATE and in terms of interview. Then I will show you that how this beautiful equation can make your preparation simpler. Then I will talk about some interview questions which I was asked during my interview in DRDO and ISRO. Finally, I will solve a sample question which was asked in GATE 2024 in engineering science to show you that yes, GATE is asking the questions directly from the application of Navier-Stokes equation. After that, you will also have 3 assignment questions, the solutions of which I will be uploading within 1 week of publication of this video. So stay tuned. Now, before starting the actual thing, I have a small request for you. This is something very new, right? So I need to know that if my audience is liking this thing or not. So please put a comment that please bring the videos for other topics also, which are very much important in terms of GATE and in terms of interview. If I see that the response for this video is not good, then I will discontinue this series. Or otherwise, if you are interested in this, then we will have a great journey. Okay. And if you are new to this channel, then I should tell you that I always bring videos on these innovative things that are not being told anywhere in YouTube, almost anywhere in YouTube. So please subscribe my channel. Itna to banta hai na? So let's meet the beautiful hot and curvy Navier-Stokes equation. A brief intro to NS equation. Don't worry, I will not give the hefty derivation. So first of all, let us see that how does it look. I think that most of us know, but there is something else that I need to tell. So the vector form is rho into del v del t plus v dot del into v, or v dot del operated on v, not into v actually. So this is equal to minus grad p plus mu into del square v plus, that will be lambda plus mu by 3, right, into gradient of divergence of v, okay, plus the body force. Okay. Now I know that most of you have studied only these terms, this term, these two, and this thing. But this term is also there. You cannot neglect this term. So if I ask you that how you can go from this equation to the equation that you already know. Okay. So firstly, what I will be doing is I will be writing this equation in x coordinate only. So x momentum equation. Okay, so rho to del u del t plus, okay, u del u del x, right? Then what? V del u del y plus w del u del z. That will be minus del p del x plus mu into del 2u del x2 plus del u del 2u del y2. So I am just writing this equation to give a live feeling. Okay, you can skip or you can just watch it in 2x speed plus rho f bx. Right? You have seen only this equation, and now let me write the additional term. That is the lambda plus mu by 3 into. So what this term will be? This will be del x of del u del x plus del v del y. Okay, del v del y plus del w del z. Clear? Okay. So now can you tell me that in which condition you can neglect this term? In which condition you can neglect this term? The answer is that when the flow is incompressible. Right? So that means if the flow is incompressible, then I can say that my this term is 0. Then I can say this term is 0. Then only I can write. Then only I can write my Navier-Stokes equation is this. So these things are very important. Okay, because you need to understand that gate is changing. The pattern of gate is changing. So they can ask you the questions where the flow is not incompressible. Okay, so this is the actual Navier-Stokes equation. Now, what does each term mean? So we know that this is what? This term is the temporal acceleration, right? Temporal acceleration. Okay, and this term is what? Convective acceleration. Okay, this term is very simple. That is the pressure gradient. Pressure gradient. See, I don't want to teach here the Navier-Stokes equation again. That is why I will be doing the things a bit faster. But if you think that okay, bhaiya, we are liking your teaching and we want that you bring the full derivation of Navier-Stokes equation, then I can do something for you. But in this video, I am not going to do that thing. Okay. So now this thing is the stress part. Okay. It is the shear stresses, or I should say the surface force, maybe. Okay. So stress, viscous stress. And we all know that this is what? The body force. Okay. And finally, this term is also the normal stress, and so this is also a part of the viscous stress. Actually, it is not a part of viscous stress. This I should say that this is due to a change in volume. Because you see, this term is divergence of V, and that is nothing but the volumetric strain rate. So now you have to understand that all this term has a unit of force per unit volume. All these terms. So unit of each term, that is Newton per meter cube. Okay, fine. So what does each term mean? That is over. Now, assumption and their significance. This is the most important part in terms of gate and interview both. Okay, so let us quickly go through that. So the first assumption, that is the continuum hypothesis should be valid. Okay, and why that is so? If the continuum hypothesis is valid, then only you can apply the differential equation at each and every point, because then only you can consider the fluid or the solid as a continuous media. Okay, so I have talked about the significance also. Then what we should have? We should have that the fluid should not sustain any body couple. You know that is why? Because there is a thing, that is tau xy equal to tau yx. Similarly, tau xz equal to tau zx. You have also studied this in the solid mechanics. This thing will be ensured if the fluid element will not sustain any body couple. I will not go very deep into this. Next, the fluid should be homogeneous plus isotropic. Okay. Next, the fluid should be a Newtonian fluid. Lastly, the fluid should be a Stokesian fluid. Don't worry, I will tell the significances. Now, these two things will directly lead us to the Newton's law of viscosity. Okay, that is nothing but tau is equal to, that is a stress tensor, is equal to minus P into I, that is the identity tensor, plus 2 mu into the strain rate tensor, plus, okay, lambda into the trace of strain rate tensor into I. So I know if you are not understanding this thing because you have not read the derivation of Navier-Stokes equation, then might be you are thinking that, I mean, what is this? This is nothing but the actual form of the Newton's law of viscosity. Then what is Stokesian fluid? Stokesian fluid is something for which this happens. So 2 mu by 3 plus lambda is equal to 0. See, you have one variable lambda here. So this is called actually the volumetric dilation coefficient. Now, how can you find the value of lambda in terms of the known quantity, that is the viscosity? That you can find if the Stokesian fluid assumption is taken. Then lambda is equal to minus 2 mu by 3. Okay, let me see if any other assumption is remaining or not. Okay, these are the 5 assumptions that you need to take care about. If you are thinking that, okay, I don't need that, I just need these things, then just bear with me until the interview questions come. Okay. And if you are thinking that, okay, how can I memorize this? Then the only way is that you need to go through the derivation of Navier-Stokes equation. Go to the NPTEL lecture of Professor Suman Chakraborty that I have already told in the video, where I have told all the sources which are free and tested by GATE AIR 31, not 1. Okay, so this was the assumption part and their significance. Clear? Now let me directly go to the part, the most interesting part I know, that how Navier-Stokes equation can make your preparation simpler. See, in GATE as well as in interview, all the assumptions, that is in which conditions the particular expressions or the particular equations are important. We have so many equations: Euler, Bernoulli, Navier-Stokes, Stokes equation, boundary layer equations. So which equations are applicable in which conditions? Okay, so I will tell you that you need to memorize only one equation, that is the Navier-Stokes equation. You don't need to memorize all those equations. And if you do this, you will have the twofold benefits. First, you will be able to recall or derive all the equations from Navier-Stokes equation within a matter of seconds, and also automatically you will be memorizing the assumptions or the conditions at which those particular equations are valid. So let us first go to the Euler equation. So in Euler equation, what we will have is this term. This term will be dropped out. Why? Because Euler equation is the F equal to ma for inviscid fluids. Okay. Or I should say where the viscous stresses are not important. Okay. See, you now don't need to memorize the Euler's equation. You can always memorize the Navier-Stokes equation. Now, if you know that the viscous term is not important for Euler equation, then now you don't need to memorize the Euler equation. This kind of mentality is very important. The least you can memorize, the better is for you. Now you see, you again, I have already told that you have two benefits. You don't need to now memorize the Euler equation, and if you memorize like this, that how from Navier-Stokes equation the Euler equation is coming, then you know this assumption also. And all the other assumptions which were valid for this Navier-Stokes equation are valid for the Euler equation also. Continuum hypothesis. Now these things will again not be valid because we don't have a tau for Euler equation. And you know that because you know that the viscous stresses are not important. That means we don't have a tau. That means this assumption 2 will also be dropped out. But okay, now these things will also not be important because again we have a tau to have these things. Here we have a mu in Stokesian fluid. You see that you have threefold benefits. That if you study like this, that how from Navier-Stokes equation viscous, I mean if I drop the viscous stresses because the viscous stresses are not important for Euler equation, then I don't have to memorize the Euler equation. I know that in which conditions the Euler equation is valid. Only the continuum hypothesis has to be valid. No other constant is there. So let us go to the Stokes equation. So in Stokes equation, this term will be dropped out. Okay, this term will be 0. So when the inertial term is not important. I know that most of you have not heard about the Stokes equation, but this is a very important equation in terms of fluid mechanics. Okay, now let us see the which maybe the Bernoulli equation. So for Bernoulli's equation, you know that the viscous term should again not be important, right? So this term will be dropped out, and you have to after that integrate the whole equation. Plus incompressible fluid not flow. For flow also this will be valid. Okay. After that, if you integrate, then you will get the Bernoulli's equation. So these are the concepts that are very important. Fourth, okay, so we have studied the Stokes equation, the Euler equation, the Bernoulli's equation. Now let us study the fluid statics equation. See, in fluid statics, the fluid is not having any velocity. So therefore, this term will be 0 because we have u here and u is 0, right? Again, this term will also be 0. See, you have this equation, which is the equation for fluid statics, right? That is minus, okay, is equal to plus rho g. Okay, see, fluid statics, we got the fluid statics thing. Okay, finally, actually, I should say that this is a most general equation for fluid statics, because see, this gx can be anything other than gravity also. I can say that this is something ax plus bx. So for those kind of questions where a cart is moving, so for a fluid element, the gravity is also acting and it is being accelerated, so a D'Alembert's force is also acting. That means here the gx would be something this one. Okay, if you see, so this is the most general equation for fluid statics. So if I was the teacher, then I would take an approach like this. First I will teach the Navier Stokes equation, then I will show you that see, all these things are just the childrens of Navier Stokes equation and nothing more than that. And finally, the boundary layer equation. So you see the boundary layer equations, how can we get that? Firstly, I will talk about the general boundary layer equation that is derived by Prandtl for a 2D case. So if it is 2D, then directly this W term will be dropped out. If this is 0, this will also be 0. So if it is 2D, then anything that is coming as the gradient of the z direction, that will be 0. Now, in boundary layer equation, because of a particular assumption, this term is 0. And do you know that why that is 0? That is 0 because we have the assumption this, and the REL is much greater than 1. Okay, and so this is actually the boundary layer equation. And finally, if you write the y momentum equation, then you will see that the y momentum equation will be del p del y is equal to 0. So if del p del y is equal to 0, then this becomes dp dx, and this is actually dp infinity dx, that is the variation of outside pressure, that is the free stream pressure. Okay, and this is happening because of this thing. See, from Navier-Stokes equation, you can directly write the boundary layer equation, and at the same time, you can memorize that which are the assumptions valid for boundary layer equation. That is, RE should be greater than, much greater than 1. Delta by L should be much less than 1. So these two are actually corroborating each other. Okay, and this should also happen. You can write the y momentum equation and directly you will be getting the same thing. This thing. Okay. Now, you can ask me that how can you memorize this thing? So I have not memorized this thing. See, I am not telling you that just because you are getting this thing, you don't have to study other chapters. No, you have to study all the chapters in detail. Only then you can memorize all the equations like this. In my time, I can actually recall that at first I was also taking this kind of approach, that okay, Euler equation is something different, Navier-Stokes equation is something different. So Euler equation is this, Navier-Stokes equation is this, boundary Euler equation is this. So I need to memorize these equations. But after that, I found this that no, Navier-Stokes equation is the father of all the equations. So I just have to memorize the Navier-Stokes equation, and just because I have the concepts that when the Euler equation is valid, when the viscous terms are not important, when the boundary layer equation is valid, when del 2u del x2 is not important and del p del y is 0. But you need to understand that why del 2u del x2 is not important and why del p del y is 0. How can I derive that? Only if you study that thing, then this thing will be very helpful to you. I am just showing you the train of thought that you should have to have that logical mentality that is expected from you during a research interview like Bark, ISRO or DRDO. Okay, so I don't think any other equation is remaining. I have talked about five equations. Okay, so the most important five equations. I don't think we need to take care about any other equation right now. Obviously, there are so many equations other than these also, but these are also very important equations. So now my interview questions in ISRO. So in ISRO, firstly, they asked me that we have so many equations, Euler, Navier-Stokes, right? And the boundary Euler equations. He asked me, the chairman in the interview panel, he asked me that with respect to an aerofoil, how you can apply these equations. So when these equations will be applied with respect to an aerofoil. So if I have an aerofoil like this, okay, so then there will be a boundary layer, okay, and above that I will be having the free stream, and that is the inside the BL. Okay, so inside the boundary layer, viscous stresses are important. That means I should be applying ideally the boundary layer equation, and also I can apply the Navier-Stokes equation. Outside the boundary layer, the viscous stresses are not important. That means I have to apply the Euler's equation. Okay. Secondly, they asked me, can you tell me the assumptions behind NS equation? Okay. So those of you who were thinking that okay, these kind of assumptions are never asked in GATE, they can be asked in GATE also. And in the interview, I was asked these questions. So the answer of this question I have just given. Okay. Now let me go to DRDO. So in DRDO, they first asked me that to model. So they asked me about my MTech thesis. So it was, I mean, regarding the fluid mechanics. So to model the fluid flow in your project, which equations you will use? Okay, to model the fluid flow, which equations? Right? So the answers will be continuity and Navier-Stokes. If the temperatures and thus the rho and mu are constant. Otherwise, I have to solve the energy equations also. Now, he asked me, can you simplify your equation based on your scenario? So, I was working in a micro channel and there the RE was very small. Okay, much less than 1. It was in the order of 10 to the power minus 3 or even lesser than that. So, that means the inertia terms will be 0, will be negligible. That means the Navier-Stokes equation will boil down to the Stokes equation. Then he asked me to write the Stokes equation. So you see, these concepts are very much important. Now, finally, I will be solving a sample question. This question has been asked in XE, okay, in 2024, XE fluid mechanics. They're saying that a thin film of an incompressible Newtonian liquid with an uniform thickness is flowing down on a vertical plate. The flow is driven by gravity alone. Assume zero shear stress condition at the free surface. Okay, find the maximum velocity. Now, let me draw the thing first. There will be a plate. This is a vertical plate. So let me set up the coordinate axis. This will be the y coordinate. This will be the x coordinate. And a fluid is flowing like this. So this is the free surface of the fluid. Okay. Here the G is working the gravitational force. This is the G. Okay. And the fluid is flowing. Now my first question is that if we have air here, okay, outside the fluid, So this is actually the fluid. Okay. Then can you draw the velocity profile? So how can it look? Okay. So this is actually your assignment question. Okay. I will not draw it exactly here. But they are saying assume zero shear stress condition at the free surface. That means, so if this is H, so mu into del u del y at y equals to H is 0. That means my del u del y at y equal to H, this is 0. That means at this point, the slope will be 0. Okay. So it will have something like this. So this will be the velocity profile. But if I don't have this condition given, then how can you draw the velocity profile? This is your homework. Okay. And I will obviously officially post the question after this video. And if you are thinking that these type of questions cannot be asked in GATE, you are wrong. And these are the very standard interview questions also. So start studying like that. Don't try to mug up. Okay. Because GATE is changing. Now, okay. So we have to find the maximum velocity, that is the u max. Okay. So u max we have to find. To find that, honestly, we have to find the velocity profile of u. Okay. So honestly, u max here will be u at y equals to h. For that, we need to find the expression for u. So we need to find the expression for u. Can you tell me that which component of the momentum equation I will be needing? That was the x momentum equation. So x momentum equation I can write like directly. I will be writing it in the 2D. Okay. Because and why 2D? Because it is a very thin film. It is given that it is a thin film. So if the film is very thin, that means the dimension h is much lesser than any other dimension in x and z direction. That means I can neglect this del z variation. Okay. So I will be having phi into del u del y, and that is equal to minus del p del x plus mu into this thing plus this into del y plus rho into g. We are already having that. So now let us simplify this thing. How can we simplify? Firstly, this is a steady flow. Okay. Although it is, I think, not given, but this is a steady flow. Nothing is changing with time. So you have to develop this thing, that you have to assess the situation by yourself, and you have to develop that thing, that how can I make simplification based on the practical scenario. This is actually the thing that is expected from an engineer. Okay. So now how can we do these things, simplify these things? First of all, we have to write the continuity equation also. So the continuity, okay, so the continuity equation will be this for a incompressible fluid or an incompressible flow. So this thing will be 0. So now, see, I have seen that many of the solutions of the coaching centers, they are doing okay. I can see that my V is equal to 0. That means my del V del Y is 0. That means my del U del X is 0. This is a completely wrong logic. I will not take the name of that coaching center. I mean, the solution of which I have read and this was being given. So this is a totally wrong concept. That's why I don't bet on any coaching center. Okay, I bet on NPTEL lectures. So the actual concept is that how can you say that inside this region the fluid will not flow like this? How can you say with so confidence? Okay, but what I can say is, if you see the actual scenario, so what does happen is that if we have something like a inclined plate and over that a fluid is flowing like this, okay, and plate is inclined and over that a fluid is flowing like this, so then this height h will actually vary with x and it will be decreasing, but after a particular distance this height will be constant and the fluid flow will not vary with x. Okay, so this will be a kind of fully developed flow. Okay, kind of, or this variation del u del x will be very small, and that is why we can write this del u del x is equal to 0. In terms of mathematics, this also will be called the translational invariance. In x direction, there will be no variation. So, and now if we apply this into the continuity equation, we will be having del v del y is equal to 0. That means v is a function of x, but v is not a function of x, we know. That means v has to be a constant. Why v is not a function of x? Because of the translational invariance. Now we know at y equal to 0, my v is equal to 0. Why? Because of the no penetration condition at this wall. So that means my v is also a constant, and at y equal to 0, my v equal to 0. That means my v equal to 0 everywhere. This should be the actual concept. Now if my v is equal to 0, then this term is 0, right? If my del u del x is 0, then this term is 0. If my del u del x is 0, then this term is again 0, right? Then the equation boils down to, okay, another thing. This flow is open to atmosphere. So you can say that everywhere it is the PATM. Okay, so the pressure is not varying. That means this del P del X will go to 0 because it is open to atmosphere. Okay, that means I will be having rho G, okay, plus mu into del. So this will be the governing equation. And honestly, I should have written not del but d, because u is a function of y only. So my d2u dyt is equal to minus rho g by mu, right? Let me quickly solve it. Du dy is equal to minus rho g mu y plus c1. Now we know at y equals to h, du dy is 0. If we apply this condition, so from these two conditions, I will be getting this is equal to rho g h by mu. Clear? And further, if I integrate, u is equal to minus rho g y square by 2 mu plus c1, we know rho g h by mu, okay, into y plus c2. How can we find C2? At y equal to 0, u is equal to 0. Why? No slip condition. At wall, we will be having the no slip condition, right? So that is why we will be getting from these two, you just put those and we will be getting C2 equal to 0. Now, if you put u at y equal to h, that is equal to u max, that will be rho g h square by 2 mu. So this will be the answer. Okay. So this is all about this video. Now you should have some key takeaways. So I made this video mainly to show you the mentality that you should have to to make your preparation journey simpler. Okay, that is, see the things very deeply. I mean, don't see the things very superficially. Like, this is the Euler equation, fine. This is the Navier Stokes equation, fine. This is the Bernoulli's equation, fine. No, try to see the links. If you try to see the links, then honestly, my friend, you will have to memorize less. And in the interviews like BART, ISRO, DRDO, even in NPCIL, they expect something like this. You have to grow up this mentality. So if you are liking this video, that okay, we need this kind of videos more and more, please put that in the comment box. Only then I will do this again for any other topic. So next topic will be maybe the boundary layer theory itself. Okay, how can we study that? And I will also show you how can you link the fluid mechanics with solid mechanics, the solid mechanics with manufacturing, all those things. I will show you. Okay, and further I will be also solving the questions asked in BARC. Okay, so if you are thinking that this guy is doing something for us, at least he is trying something for us, then प्लीज यार एक सब्सक्राइब कर दो. सो इससे क्या होता है, ऑनेस्टली मोटिवेशन मिलता है. तुम सभी जानते हो, ये सभी मतलब यूट्यूबर्स का कॉमन डायलॉग है और ये सही है. मतलब बहुत मोटिवेशन मिलता है जैसे कि तुम लोग कमेंट्स करते हो. एंड आई विल बी ऑनेस्ट दैट यस, अर्निंग मनी इज वन थिंग दैट आई वांट फ्रॉम दिस YouTube channel, but not at the cost of your happiness or your well-being. I will not I will not fake anything, for sure. If I make any mistake, then you can always tell me. I will accept that. If you are thinking that, okay, this guy is doing something else, okay, just for making money. No, I don't want that. I want to make money, but at the same time, I want to make sure that I am helping my YouTube family. Okay. So if you're interested in some research interviews, because after this kind of videos, I think that you might be thinking, okay, so now this is something interesting, and you have also seen the research interview questions. So then the full DRDO interview experience is here in front of 5 research scientists of DRDO. So I will meet you in that video. Until that, goodbye, take care, and thank you.